Welcome again, guys. In this video we are trying to prove this logical expression. So we're trying to prove that P or not, into brackets, not P implies Q is logically equivalent to Q not to Q implies P rather. So we're trying to prove that what is on the left hand side is logically equivalent to what is on the right hand side. All right, so before we even start to prove this expression, what I expect you to at least have an idea of is the concept of implication, right? So this is implication. This means that if A implies B, this is logically equivalent to not A or B. So I need you to know this. If you don't know this, then just comment down below and I'll release a video explaining implication, just a short video explaining implication. And then another thing that I expect you to know is De Morgan's laws. So I need you to know what De Morgan's laws are. So right, just a basic understanding of De Morgan's. And then I also need you to understand the concepts of contradiction and tautology. So I need you to at least know what a contradiction is and what a tautology is, and in case of a logical expression, so in case of logic, so to speak. So these are the things that I expect you to know. So implication, De Morgan's laws, contradiction, and tautology. That means knowing some of the identities of tautology, some of the identities of contradiction. And let's not waste too much time and let's start with the proof. Right, so to start with the proof, we're going to take the left hand side. So the left hand side, we have P or not P implies P, right? So that's our left hand side, right? So using implication, we can break this into something that is understandable. Remember that implication is if A implies B, this is logically equivalent to not A or B, right? So we can simplify this into something palatable using the implication rule. So this means that we'll have P or not. Now, if we want this to resemble this means that we're going to have a not and a not P, because our P is the first thing that is on the left hand side. That is our first thing, or what is on the right, which is P in this case. So we have P like that, and therefore we'll have P or not, and then the P's now, the negation, cancel each other out. I made a mistake of writing P here. Let me just erase this because that will cause a lot of problems. I made a mistake of writing P instead of Q. This is supposed to be Q. Apologies for that. That is Q. Therefore, the negations will cancel each other out, and we'll be left with P or Q like that, right? And then now we're going to distribute this negation inside. So when we distribute a negation inside, we're going to have P or not P. When we distribute a negation, the joining symbol changes. So this means this will no longer be an or, it will be an and therefore not Q like that. And then now let's distribute this P across these terms. Therefore, we're going to say P or not P, and we have a bracket right there because we're distributing this there and we're also distributing this there. So it's P or not P and P or not Q, right? So we have that. So P or not P and P or not Q. So if we have something like this, you can see that we have P and P or not P. They are all P, like they're related because they are of P, but this one is not negated and this one is negated, right? So this one is a tautology because whatever combination of truth value statements, this one will always result in true, right? So the truth value will always be true. So this is what we call a tautology, and we're going to replace a tautology with a TT, which stands for a tautology that returns it returns true for all truth values. So that's why it's a TT. That this is a tautology, and therefore we can replace it with that and say TT and P or not Q. Right. So one of the identities of a tautology, or identities of annihilation, so to speak, is that if you have a tautology and then you drop a tautology. That means that if you have a tautology and an and joining symbol, that means the tautology is allowed to be dropped, right? So we can annihilate the tautology and we'll be left with P or not Q. Remember that we are trying to make it logically equivalent to Q implies P. All right, so this should not be an equal sign, by the way. This should be logically equivalence. This should be logical equivalence. So now using implication, let me just rewrite this starting with the negated one. So we're going to have not Q or P because we're allowed to do that. We're just rearranging them. So using implication again, let's rewrite it again. Logical equivalence, not A or B. Now if you look at this, let this one be our A and this one be our B, right? That means that if you have not Q, this is the same as not A, or P, which is not B, which is similar to this, which means we can rewrite this in this way. That means Q implies P. And if you look at our expression, that's what we were supposed to prove, that it's logically equivalent to Q implies P. And therefore, this is equal to the right-hand side. And we have proven that whatever is on the left-hand side is logically equivalent to the right-hand side. I hope this video was useful, and I hope you found value in it. So be sure to like and subscribe and share this video so that you help the channel grow, and I will see you in the next video.